Hi, this is Dr. Joe Chow speaking. Uh, Today, I would like to talk about this PAMPA dissolution in terms of BE formulation. Mm, because by tradition, this topic is always BE formulation is always based on the traditional uh, pilot bio study. However, the pilot bio study includes uh, usually 10 to 12 subjects um, drug absorption, excuse me. However, based on these 10 to 12 people, it includes also the subjects variation. So therefore, in order to exclude this variation so that this PAMPA dissolution might, give us a help in terms of drug B formulation. Let's take a look. Okay. Before starting, I would like to talk about my personal biota in terms of I was working in Sandoz Pharmaceutical as a generic drug R&D manager. Prior to that, I worked for Pfizer as a new drug analytical scientist and also as an adjunct professor at New Jersey Institute of Technology. We've been doing like about 60 in the drug successful filing. And because of these past experience, make us understanding that in generic drug uh, formulation development, we 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 do need a good instrumentation to mimic human GI tract, and therefore it will be able to exclude the variation from test subject and purely just compare the reference drug versus test drug in the laboratory. So that will shorten the R&D resources in terms of the drug development, right? Okay, first of all, before we started, we would like to talk about some this BCS classification and drug absorption theory. Initially, 1991, this theory was really proposed and being also verified through this mass balance of drug in and out of, let's say, a test like a small intestine with a length of L. So in the previous YouTube, we have talked about this this development. However, here we want to repeat, like briefly repeat about this. If you have a drug, let's say coming from left side, in terms of drug mass in milligram per hour, going in through the length of L of small intestine, and coming out as drug mass hour rate milligram per hour in terms of like Q times Cm. In is Q times C0. Okay, so based on mass balance, we know that whatever comes in minus whatever goes out plus minus this one, it will be like equal. That means like mass is balanced. Whatever comes in should be equal whatever goes out from two directions, right? So based on this, we can really figure out the first equation, which is like drug from the left side and drug from the right side. So that means in minus out equal absorption. Okay, so the absorption, there is a so-called JW. So that JW actually is drug flux. So after integration of first equation, you will arrive with F equal JW times A. However, JW is a wall flux of the drug, and A is absorption area. Okay, so we can further like figuring out what is JW is actually equal CB times PE. CB is the drug concentration, which is the dissolution that everybody are doing it as a RD scientist every day, and PE is the permeation of the drug through small intestine. Okay, so by substituting these CB and PE into equation 2, you will end up with this equation, which is F is a drug absorbed equal CB times PE times A, and A is a surface area of small intestine. Okay, so with this understanding, that's back from 1991. Yet in 1995, this BCS classification was proposed and later accepted by United States FDA, meaning like there are 4 types of drug will be classified according to their permeation and their solubility. Okay, so by comparing these 2 systems, you know that actually the drug absorbed is really following this equation, and actually this equation is also being validated through like several scientists in the past 30 years. So we know that since this is valid, there are variable inside the equation as CB and as PE. Consider this area, small intestine surface area, as a constant, then we can really figuring out that we need an instrumentation to be able to measure the PE and measure the CB. Okay, these 2 variables, and therefore in 2020 we developed this instrumentation, so-called PAMPA dissolution, able to measure simultaneously these 2 variables, and therefore able to predict these drug equivalence. Okay, all right, let's take a look at the next one is development of this PAMPA. Ideally, PAMPA was developed for 30 years in scientists journal publication, right? And these idea is really adapt from this KCO2 to PAMPA. And why scientists want to do PAMPA way, it's obviously if you are doing KCO2, the reproducible of the KCO2 is a major problem. So that in terms of like reproducibility and or applicability, it will be very difficult because usually it takes like 20 to 30 days to incubate this KCO2 before you can use it, and therefore it will delay these R&D process, right? And therefore scientists back 30 years ago starting try to find out a way, it's called PAMPA, to substitute these KCO2 cells. And therefore from this figure, as you can see, this drug in the small intestine being absorbed and being transported in blood circulation, right? However, the absorption is really based on this small intestine surface configuration. And based on this configuration, scientists figure out that we can use a membrane coating with phospholipid, and by overcome these so-called undisturbed water layer, UWL, and therefore with that UWL being like clarified as if the UWL, if it is stagnant, meaning is not agitated, it will be 1500, which is 1500 nanometer. Okay, and the real situation in the small intestine is really in the ballpark of 100 to 300 nanometer. So that means like both sides of dissolution media and the absorption, which is plasma area, in the both area, it needs to be stirred so that this UWL will meet that range. Okay, that's what scientists through 30 years discussion, they have come up with so-called PAMPA. That's the configuration. So that after 30 years, this PAMPA is mature, and therefore in combination with this dissolution, so that we can come up with PAMPA dissolution, able to predict these bioequivalence easily in the laboratory. Okay, to meet that requirement, so first of all, we had to make sure that the dissolution is really following the GI tract of human. Okay, so as you can see from the graph here, it indicates these pH versus hour for these human GI tract pH change. Okay, so initially about half an hour also, that's the drop pH in the stomach. So it's about pH 1.5, 1.6 that range. It's not 1.0, not 1.2. And once that after half an hour, once the solution goes to a small intestine area, it will change the pH drastically to about 6 to 7. So we take an average value of 6.5 to mimic the small intestine pH. Okay, so in terms of the pH change with respect to time, this was done by these United States Institution of National Health. Okay, and so that with these major pH, so we know how to control the pH of the stomach within 30 minutes, and later with this FASSIF for 30 to 90 minutes. But why is that we need to use fasting state simulated gastric fluid? It's really after scientists study for this stomach fasting state fluid for about 10 to 20 years or so in that ballpark, so that scientists already agreed to use that instead of like buffer. Okay, if you use a buffer to do the simulation or mimic to the human stomach situation, you may have some deviation. Okay, so use FASSGF, and in addition, we will add this FASSIF in the time sequence and volumes, like this, 400 initially and 100 for the 30 to 90 minutes. Okay, so in addition to that, sometimes you can use 250 ml mini vessel. That can be used also. Okay, and also we will pick the right pedal speed, which is around 50 to 75 RPM. Okay, and basket will be 75 to 100 RPM. And these are all been like verified through scientist study. Okay, to mimic this human GI tract condition. And such a the fasting state gastric fluid and the fasting state intestinal fluid, the powder can be purchased from that or other manufacturers. Okay, but these two components, they are very easy to prepare and commercially available. Okay, now let's talk about the system. With that, CB can be monitored or measured easily through the so-called biomimic media, and we can use in the dissolution vessel as those biorhythm media. Okay, so instead of using buffer, so with that biorhythm media, the drug can be dropped into the dissolution vessel and being literally dissolved and pumped through the pump to the lower PAMPA. What the PAMPA does is that the active in the dissolution can be permeate through the white membrane, which is the PAMPA membrane, and arrive to the pink area, which is the plasma. So once that drug permeate to the PAMPA area, it will be to the plasma area. It will be measured by fiber optics. Okay, so that both parameter. One is dissolution, which is CB, or permeation, which is PE. Both are monitored through fiber optics in this PAMPA dissolution. Okay, so that with that, we are using the biorhythm media. Let's say 1, 2, 3 for reference, 4, 5, 6 for your test drug. So the average value of 1, 2, 3 versus average value of 4, 5, 6 can really give us a pretty good estimation about the test formulation, because everything really follow the biorhythm media and the PAMPA approach, and both technology are proven already. Okay, so it's quite reliable using such a technology in the laboratory instead of like using traditional 10 to 12 testing subject to do the pilot bio study. But as to how this formulation with PAMPA dissolution can be done, we will address this in detail. Okay, before we move ahead, there are two criteria for prediction from this PAMPA dissolution system. The first criteria is so-called Cmax, that average of T divided by R is really estimated from the slope ratio of T versus R. Similarly, this AUC, estimation, right, can be done also by this area ratio, which is the area under the curve of permeation. With these, two parameters, if they are either slope ratio or area ratio, if they can be within plus minus 20% from the brain drug, we will consider it can be proceed as this full study, okay, of the BE. Okay, all right. So before we proceed, we will understand like these criteria from the PAMPA dissolution as defined like this, so that once you done your PAMPA dissolution measurement, you will know right there what is the ratio, either slope ratio for Cmax or area ratio for your AUC. That will address this test formulation clearly. Okay. Now from this PPT, we can see something easily is that if we have the result from this PAMPA dissolution, let's say from left side is so-called tilmiston 40 milligram, and from the right side is so-called Boston 80 milligram. What's interesting is that these two are all BCS2 drugs, yet let's say the left side figure represent dissolution and right side figure represent permeation for first drug, tilmiston. And you will see this dissolution wise, the curve for the red one, which is Mycotis as a reference, and the fourth one is the generic drug. The dissolution, they are fairly close. Yet this permeation-wise, a little bit deviate of this Fosun's drug from this red one, which is the brain drug reference Mycotis. However, this can be really done through this estimation, right? As we talked already about the slope of, let's say, data point of red or data point of blue beyond, let's say, the force point, because beyond force point, everything like getting permeated drastically, right? Prior to that, it's fairly nothing permeated for telmisartan. But in this case, to do this understanding of why the drug tend to be really permeated through maybe alkaline media, because we know that initially the S media mimic the stomach. The drug does not permeate. However, once that the drug pH change to 6.5, then we will see they are changing like drastically in permeation, right? So by analyzing carefully through this telmisartan solubility table, we can conclude with this result. As everybody can see from this pH versus solubility table, you can easily figuring out the telmisartan at pH 1.2 has higher solubility than pH 6.8, right? So more or less we can come up with a conclusion like this. At higher solubility, this drug will give lower permeability, right, as the permeation shown. However, at pH 6.8, at the medium solubility range, it gives a higher permeability. However, if you see from this Fosuntan, its permeation looks like the opposite way, meaning like in acid, it permeates fast, okay? And however, in pH 6.8, it tends to be like permeate slowly, okay? So why is that? As you can see, at pH 1.2, their solubility is within that medium solubility range, so that within certain range of solubility that will make this permeability becomes like more feasible than the higher solubility. Okay, so as you can see, the medium solubility means like 12 to 90 gives higher PE. However, at pH maybe 6.8, it gives like higher solubility. From here, as you can see, 200 is much greater than 90, gives lower permeation. So these two give us a hint is that if you want to do a BCS2 drug formulation well, you had to watch about the pH effect. Okay, and definitely in addition to that, if you are using any solubilizer like PVK30, HPMC, HPEC, Salupus, beta-cyclodextrin, those solubilizer, if you are using any solubility enhancer, you need to watch out. Those might giving you like might be higher than expected permeation, because the solubilizer not only will help this permeation, right? This pH wise will also dominate this permeation. So if you add these two together, your formulation could be higher than expected, with different like solubilizer and different process. Okay, so that's just purely for the bioequivalence requirement. So if without such an instrument like PAMPA dissolution, if without this instrumentation, then you need to do your process versus, let's say, pilot bio study using 10 subjects again and again, back and forth several times, then you will finally get something, right? Which you might think is reliable. However, if you really get to the full study, the result may not be, as you expected. So in order to overcome such a problem, maybe, we can use this PAMPA dissolution, and it's exactly following whatever requirement from the GI check of human, right? So with these, then we will save lots of time and money, in terms of arriving the bioequivalence drug, right? Okay, so these two are the illustration showing the BCS2 drug. We need to watch out the pH-dependent circumstance, okay? And in addition to that, like I just described about the effect from the stabilizer, because drug usually, in this case BCS2, they tend to have a lower solubility. So scientists might want to use stabilizer to enhance this solubility, right? Look like the diagram shown here. However, once you increase the solubility, then the polarity, meaning affinity, it will change also. So that it might enhance this permeation. And therefore, in this case, if you can see from this graph, it comes out like this. The green line is marketed drug, okay? And the red line is the one with solubilizer B, and blue one has solubilizer A. So it really shows if you have different solubilizer, as we indicate here, with a special process, in that case, you might end up with a greater permeation than the marketed drug. And therefore, your drug is like over, the marketed drug in terms of like Cmax and or AUC, right? So if you have such a PAMPA dissolution in the laboratory, then your process can be done easily with this PAMPA dissolution estimation to predict your CB or PE matching these brain drug or not easily, right? However, without that instrumentation, you will just back and forth using this like pilot bio study as the only tool to predict your test formulation. But then, time and money and risk is always there, okay? All right, second, example saying the BCS2 drug. One is etoricoxib 60 milligram. The other one is ezetimibe 10 milligram. As you can see, like the previous one, they are BCS2 drug. The dissolution from this etoricoxib drug, they are fairly close for the reference and test. However, their permeation, as you can see, they are fairly overlapping for Akosia and Eto. And this is very interesting phenomena as this drug is having a log P around 2.79. That means while it's hydrophobic drug, however, it's a little bit less hydrophobic. Okay, usually the log P, if it's greater than 3, would consider this is a very hydrophobic drug. Okay, like the right-hand side one. Okay. The right-hand side ezetimibe has a log P 4.5, so it's highly hydrophobic drug. And by compare these two pH solubility, you can see that the solubility of ezetimibe, they are all lower than like we indicate previously, 12 microgram per ml. As you can see, their solubility is low in isotopic case. However, in heterocursive case, you will see the pH 1.2 for that drug, the solubility is lower than 12, and antibody is like the low solubility. Okay. However, if it is like in the medium, means like 12 to 90 microgram per ml, it tend to be give higher PE. All right. So as we discussed previously, this will give us a low initially permeation and high later permeation. However, this ezetimibe does not have that medium range of solubility, so it always gives us a low solubility according to these permeated mass. You can see is almost like 0.0 something range, 0.03. Here is 0.4 or to 0.7, that range. So obviously these two drugs has a lot different in terms of permeability, about 10 times different. Okay, so it really have some interrelation to the pH effect, okay, of the drug, and definitely has some effect from this solubility included in the drug formulation. So therefore, with this PAMPA dissolution, it can tell us easily, right? However, without this, again, we will need to use human like pilot bio study back and forth several times, and that wastes our time and money. Okay, so that's what the purpose for this instrumentation, to help scientists determine the formulation easily, right? Okay, with these two like cases indicating the BCS2 drug can be done through the PAMPA dissolution as a formulation selection. Okay, and initially, well, the drug absorption follow this equation, so that we understand there are two parameters need to be resolved during the formulation R&D. And now in terms of the PE, right, we can see these API solubility. If it is pH dependent, then this solubility will affect the pH, as we shown on the upper two cases. And further is that the particle size of the API will definitely affect the solution, and that the solution will definitely affect the PE. Therefore, the particle size of those BCS2 drug is a determinant also. Not only this pH, also this particle size plus the excipient and process. Okay, so you have different solubilizer or different process. Let's say if you are using the dry or wet or even solid dispersion, those three are commonly used in BCS2 drug. Those process plus different excipients, these are all affecting the PE. So with all these together, you had to be really careful adjusting these parameters to arrive with a bioequivalent formulation. In addition, in terms of testing, by tradition, we are using buffer solution, but that buffer solution is really not as close or as possible to the human GI tract. Therefore, we are recommending using the viral media, which is the FASSGF for stomach and FASSIF for intestine into the dissolution. Plus this PAMPA that really can help arriving the BE faster. Okay, and if in case the test drug does not meet the RLD in PAMPA dissolution, simply reformulate test with the, the B, CB, and PE acquired in the prior PAMPA dissolution. So with these two parameters really well monitor through this PAMPA dissolution, we are very confident that this PE formulation can be arrived easily, as you can see from the previous two charts. It indicates, okay. Okay, to kind of compare these two methods in terms of like PE prediction of traditional versus PAMPA. The left side is traditional way. And in the traditional way, we usually use about 10 subjects and takes maybe 60 days to get this bioequivalence of T versus R data. However, this B data, including these formulation plus subject variation, right? In terms of like modifying your formulation, then sometimes you will end up with question because you don't really know this is because of formulation different or because of the subject variation difference that cause the BE difference, right? So although sometimes you can get a pretty good feeling, but about 50% and up, you will have like question in terms of like formulation study. So instead of using these traditional way, we use today's PAMPA dissolution that will help us resolve the subject variation problem, because in this test there's no subject, it's only machine. So whatever measure is really the formulation variation, right? There's no subject variation. So whatever we measure, then we can adjust the formulation according to the CB and PE easily, right? So that with these, we can do the this formulation screening in the laboratory in a much faster way to arrive the PE formulation. Okay, now I would like to make a conclusion of this PAMPA dissolution. PAMPA dissolution can not only apply to the generic drug prediction of the Cmax and AUC, well, definitely with RLD. So, you can compare them using the PAMPA dissolution easily, 3 versus 3 tablet, right? And in addition to that, if we want to do the 505B2 drug, yes, because 505B2 also having this IOD, right? So that can be applied in terms of drug absorption and AUC prediction of 505B2. And to the last is the new drug application. Yes, although it's without IOD, but we can still using the approval database to help predicting, because this approval drug database has characteristic of these PK values, right? So with the database help, and we can end up with closer IOD, and using the IOD that we can predict your new drug formulation, okay, in PAMPA dissolution. Okay, so that's it for today's formulation using PAMPA dissolution as a base to predict your drug formulation performance, okay? If you have any question, you're more than welcome to contact me through email or my cell phone, and wish you have a good day. Thank you very much. Bye-bye.